Introduction to projectiles and projectile motion. First of all, let's define what we mean by a projectile. A projectile is an object that is launched with an immediate force, but then immediately after that launch, there is no other forces acting other than the force of gravity. So I'll give you an example here. If you kick a football off the ground, you immediately kick the football, and your foot gives it an initial force, which results in a quick acceleration, and so the football has a velocity now. But once it leaves your foot, it travels in its path up into the air and back down again. And while it's traveling, from the moment it leaves your foot to the moment that it falls, no other forces are acting on the football except for the force of gravity. And so projectiles are only under the influence of gravity. But they have their characteristic shape because they do continue to have some velocity sideways velocity, but there are no sideways forces. The contrast to that would be, a little, let's say a model airplane. Well, a little model airplane has an engine. And so when the model airplane propeller spins around, this engine is going to be able to constantly apply forces. So when the airplane launches, it might go this way, but it can spin this way and turn back this way, and it can constantly change its motion. And obviously this is not what we mean by a projectile, right? And then it crashes over here in a giant fireball, and it's the end of the model airplane, right? I saw a video the other day of this guy who got a brand new model airplane, went out to the field, and he was all excited. It probably cost him $800, and he launched it into the air, and the plane came around and immediately crashed into the ground behind him and was destroyed. The maiden flight. That's not a projectile, because forces can be applied to it, aside from gravity, all through the flight. All right, so now that we know what a projectile is, let's look more closely at this shape. Let me draw that ground again. And our football. And we know that if we kick a football, it goes up into the air, and it follows this arcing path. And this arcing path has a very specific shape. It is the shape of a parabola, which you know from math, parabola. In fact, this is sometimes called parabolic motion. Projectiles move with parabolic motion. That's the shape. Now, if we go back to our math class, just for a minute, because it's always good to associate the math we learn with what we're using it for. Remember that the simplest parabola equation is y equals x squared. And if we draw a simple little table of values, x and y, and we'll put in some numbers here, -4, -3, -2, -1, 0, 1, 2, 3, and then we'll calculate the y values. Now remember, y equals x squared, so this would become 16, this would be 9, this would be 4, 1, 0, 1, 4, 9. We could add our positive 4 in there for symmetry there. Now look closely at the way the function moves. On the x column, you are stepping up each time by adding 1. Each movement in x is a constant movement. It's only moving by +1, and that never changes all the way through the entire function. But if you look at what's happening with the y value, let's start at 0 first. You're moving here, that looks like +1. But then the next step looks like +3. And then the next step looks like +5. Right? And the next step is +7. So you notice that your rate of moving is increasing. Increasing each time. Whereas over here, The movement is constant. So a parabola is a great mathematical model to model something that is moving constantly in one direction, but is increasing or decreasing in an exponential way. And if we think about velocity, we would have constant velocity here on the x side, and on the y side, a changing velocity, which is an acceleration. So this is a great model for something that has acceleration on one dimension of its motion and constant velocity on the other. And if we look at the example of our projectile, we notice that it has the force of gravity on the y, g, well, let's call it fg, which gives us an acceleration of negative 9.8 meters per second squared. But if we look at moving sideways, there are no forces pushing sideways, no significant forces. It's true that there would be some air resistance pushing back, but because air resistance is, for the most part, on large objects, for the most part in the realm of what we do, it can be kind of ignored. The other problem is it's also difficult to calculate because air is so ununiform. Parts are hotter, parts are cooler, density, water vapor, all these things. So we can ignore the air resistance, so it's safe to say then that there are no significant forces. That means that this is constant speed. So you can see why this takes the shape of a parabola. Mother Nature understands all this math, and when you kick a football, she knows that this football will automatically trace out the path of a parabola because that's the math that describes its position. Parabolas have squared terms in them, and you will notice that the equations we're about to use to describe these will also have squared terms in them for the vertical motion when the gravity is involved. So let's take a projectile and start looking at some numbers and how we might formulate a solution. So first of all, let's talk about what we would like to figure out. Let's go back to our football question. Here's a football, and suppose you're a receiver. Your job is to catch this football, to run it. This is the kickoff. You have to catch this ball and run it back up the field. Being in the right place where the football is supposedly going to land is kind of important to you. So the football will be kicked, and it will land somewhere over here. So what you would like to know is, how far is this? What is this horizontal distance away from where the football was kicked, which we call the range of the equation. The range is the horizontal or the x displacement, the displacement sideways. You aren't too concerned about how high the football goes, so you're not really concerned about the height, the vertical displacement. You're only concerned about the horizontal displacement because that's where you have to be. Right? Okay, so we're going to try to find the range of this projectile. To do that, we're going to have to give our projectile some numbers. When we kick this football, we're going to kick the football with an initial velocity called v. And we're going to use 20 meters per second. And we'll put that right down to the axis. So now, the other thing we need to know about this vector is we have its magnitude, we need to know its direction. So we will give this an angle, and we'll use the angle 60 degrees. All right. Now, what we're going to do is we use our trick of breaking up this vector into its horizontal and vertical components. What we need to know is how much of this red line is uppy-downy and how much is lefty-righty. So let's draw in the components of this vector that are horizontal and vertical. The horizontal one would go right about there, and that's how much sideways motion we have in this initial velocity that we're kicking with. And then the vertical would be this here. Notice that these vectors are tip to tail and at 90 degrees, and they begin and they finish with the red vector. So the blue line plus the green line equals the red line. So we've replaced our 20 meters per second speed with two other velocities. And we can calculate them because we know that from trigonometry, this will be 20. It's opposite the 60, so it will be 20 sine 60. And sine 60 is about 0.87. So if we multiply 20 by 0.87, we get about 17.3-ish. Very good. So that represents how much of the 20 meters per second is moving the ball upwards. And if we go down to the bottom here, this bottom vector, I'll do it over here so it's not confusing, would be 20. It's adjacent to the angle, so it's 20 cosine of 60. And we should probably put in our little 60 degrees. Remember, you have to have your calculator in degree mode all the time when doing this kind of trig, not radians or gradians. Be careful of that. Cos of 60 is a half, so this works out to about 10, correct? Good. So if you kick a ball at 20 meters per second at an angle of 60 degrees, then what that means is it's exactly the same as if you could kick it straight up at 17.3 meters per second and sideways at 10 meters per second at the same time. It would end up following the path that we described. So now we have the components, the x and y components. So what we'll do is, now that we're breaking this up, is we will break it up and consider the horizontal and the vertical separately. So here is the vertical information, and over here we'll write the horizontal information. Now we're just going to look at the question and try to figure out what we can from there. So back to our picture. Vertically, just looking at the up and down, we have an initial velocity. And that initial velocity is the 17.3 that we figured out. The y component of the velocity is the initial vertical, uppy-downy speed. And so we'll write in, way down here, v1 vertically is equal to 17.3. And it's also moving upwards, so that's why I'm going to use a positive 17.3. If we look at the other factors that might be happening, vertically, up and down, well, we know we have our little friend, gravity. The acceleration is negative 9.8 meters per second. Gravity is always up and down, meters per second squared. Always in the vertical. There's no gravity sideways. Gravity can't make things move sideways. Not on its own, anyway. The other thing that we might consider is there will be a certain vertical displacement, and there's obviously going to be some time involved. So these are the players, right? They're always present. Let's try to see if there's some hidden information in this picture that we have missed in terms of the vertical. The vertical displacement would be the difference in height from the start and the finish. At the start, the football is on the ground. At the end, the football is on the ground. So the difference in height is 0. There is no vertical change in height when you compare the beginning and the end. And that's an important thing to recognize. On level ground, 0 meters is the displacement. I was about to write for a second. Okay. Now that's about all we have for that. On the horizontal side of things, we have a speed, but it's not a v1 or a v2, it's the v all the time, because we said that when we move sideways, we move at a constant speed. So because it's a constant speed situation, the speed will always be the horizontal component, which is the 10, the blue line that we have drawn. So that horizontal speed is 10 meters per second. We're assuming all standard units, but I noticed I didn't write them over here by this one, so I'll write them there too. Now, of course, we will have a d, a displacement, and we will have a time. Now, the displacement, we've already written it on a picture. We said that the horizontal displacement is the range, which is the quantity that we're trying to discover. So d is the answer to our question. That's our goal. We need to figure that d out. To do that, we need to write expressions for the vertical motion and the horizontal motion. Starting with the vertical, and it really doesn't matter which one you start with, you're going to end up using these two together. In all of your projectile motion solutions, whichever unknown thing you're solving for, it will involve these two expressions some way or another. So if you start with one and don't seem to get anywhere, then you just go to the other one and hopefully something will pop up that you can use. But if we start with the vertical, notice we have an A here. So we cannot use any formula or expression that doesn't have an A in it. The one that jumps out is d equals v1t plus a half at squared. This is usually a good bet for describing the displacement vertically. And if we put in the numbers we have, the d is a 0, the v1 is 17.3, and if we put in the 9.8, where the a is, it's going to make that term negative. We also have to divide it by 2, so I'll do those 3 steps all at once, 4.9 t squared. And this is an expression that we can work with. We can actually solve for t, so we may as well just keep right on going. If we factor t out of this expression, it will be 17.3 take away 4.9t. And since this is a multiplication of 2 factors, either the t must be 0 to make this true, or the entire quantity in the brackets must be 0. So, or 17.3 minus 4.9t must be 0. If we continue to solve this, negative 4.9t equals negative 17.3. And if we divide both sides by negative 4.9, 3.5? 3.5 seconds. So this football is in the air for 3.5 seconds. This is the vertical displacement. Okay? Now, if we go back up to, that's no problem.
The electrical contractor would like to meet with the science teachers at just at the beginning of lunch, maybe more in the prep room, to explain how to turn on the power.
Okay, no
in
problem.
Science labs.
Excellent,
Okay?
thank you.
Thank you.
All right. That's live video for you. Over here, we have a constant speed situation. So d equals vt is the expression we can use. There is no acceleration in the horizontal. Now, the displacement is what we're after. That's the range. And the speed is 10. But it would sure be nice if we knew how long this football had to fly through the air. But we know that, don't we? Because the time the football is in the air is also the time that it has to move horizontally. So the times are the same. So we can do a simple substitution. D equals 10 times the time in the air. And this football is going to move horizontally 35 meters. Perhaps not the best kickoff, but that's the story that we have. So therefore, the range is 35 meters away. And the receiver, if he stood 35 meters away in the horizontal direction of the kick, he'd stand a good chance of catching the ball. That's the simple version of the projectile. In another video, we'll discuss some of the more complicated forms of solving. The beautiful thing, though, to point out, is that these equations, this one for the vertical and this one for the horizontal, contain all of the information of any projectile under these conditions. And so, whether you're solving for the A or the T, or the V1, or the D, or the T, or the V. They're all in here. And this framework will solve any of those questions. You just have to set them up, and what will happen is the variable that you're looking for will be the last one that's left to solve, as it was for us down here at the bottom. Our time, put it in, and there's the variable left to solve, in this case the range. But if we had known the range, then that D would have been a different number, and perhaps the A would be what we were solving for. And we would work out these two equations to get the solution. So this is a solution for every kind of projectile motion. And we had trouble like this before. That's the end of the video, so we're good to go.